In this video, we're going to be looking at the inverse cosine function. Now, if you recall how we defined the inverse sine function, we started with f of x equals to sine, so we're going to start with f of x equals to cosine of x. In this particular situation, you'll have to recall what the graph looks like one more time. The graph starts high, continues low, goes back up to high. That's one full period of the cycle of cosine, but we're going to go ahead and continue it further just to get a better idea of what it's going to do. If I'm trying to find the inverse cosine function, again, if I'm looking for f inverse of x equals to cosine inverse of x, you can also call it arc cosine of x. That's the same exact thing. It's just a different notation. We then have to limit the set of x values we're going to pick up here so that it's a continuous set of values. Again, in this case, we'd have to select a set of x values that will not repeat any of the y values. That's what we have to do in this situation so that when I flip this over that y equals x line, it creates an individual function that passes the vertical line test. So if I try to select anything very much like the sine function, if I start at negative pi over 2 and work my way to pi over 2, you'll notice that that actually creates one full hump, and it's going to fail that horizontal line test, and therefore will fail the vertical line test when flipped. So if I start here instead and work my way through here, 0 to pi would actually give me a set of values that's unique. And you'll notice how it looks quite similar to that of the inverse sine function when selected. Keep in mind that sine and inverse are actually just shifted functions of themselves. So the inverse cosine function should look quite similar to that of the inverse sine. So if I were to graph the inverse cosine function now, and again keep in mind that it should be more focused on the y-axis than the x-axis this time. We're going to start at the high point in the y-axis, so we're going to start at the high point in the x-axis. That's that value there. We're going to go ahead and move out to pi over 2. That pi over 2 value is the halfway marker, and then we're going to go all the way out to pi. So I'm going to go ahead and see if I can do this as accurately as possible. There might be some overlapping in the other graph. But it's going to start high, it's going to be all positive values till we hit that location, and then it's going to go ahead and it's going to decrease until we hit the -1 value right about there. So there is your cosine inverse graph. And you'll note that the domain of this one here, I'm going to go ahead and start with the x values, goes from -1 to 1, just like the sine function. And our range, the values that this cosine inverse function can spit back, will be values between 0 and pi. So the range of this is actually different than that of the sine function. Please make note of that and be very careful when working with this cosine function. So this is your graph of the cosine function, cosine inverse function. We'll notice that in the original function we will limit our domain to 0 to pi so that it appropriately correlates. Again, this is the general or the regularly accepted domain of the inverse cosine function such that it creates one unique cycle of all the possible values that cosine can obtain. So in this case, we're just going to go ahead and run through the examples one more time where we go ahead and look at a very specific type of inverse function. Let's look at the cosine inverse of radical 3 over 2. For this one, again, we're still going to look back to the unit circle because that's where we feel comfortable. I'm going to go ahead and remind us that, remember, we plug angles into the trig functions, we get angles back. We identify that this has to be equal to some kind of theta. So I'm going to go ahead and do that real quick, and then I'm going to convert it to be cosine of theta equals to radical 3 over 2. I'm going to repeat the statement I made in the sine video, is that if I was given this and I was asked to solve for theta, there's an infinite number of possible solutions for theta. But because I was given this to start and I added the theta into it, and I'm asking myself, well, when does cosine of theta equal to this? I have to stick to the domain and the range of the inverse cosine function. So in this case, I can only get values back between 0 and pi. So on my unit circle, I'm going to go ahead and focus from here to here. So in this case, sine is defined on this half of the unit circle. Cosine is defined on this half of the unit circle. So in both cases, we're still going to include that first quadrant. You just have to remember which section of values we're going to include. It might help, again, to recall that the sine function correlates to y, and we're going to go cover one full cycle of y's. And over here, we're going to go ahead and circle around the x's. So all I have to figure out now is when does the cosine of theta equal to radical 3 over 2? Well, in this case, it's that first location on the unit circle. based on the ways that, again, we use to recall that unit circle. The cosine value is the x value, so I want cosine of theta equal to radical 3 over 2. That's that radical 3 over 2. This one over here, remember, would be a negative radical 3 over 2. So that's not the value we want. So we want this one right here, and therefore the angle we're looking for based on this inverse trig function is simply pi over 6. If I were to look at another example, say the cosine inverse of, let's just go ahead and do negative 1/2. In this situation right here, again, we're going to look for an angle measure. Every inverse trig function is equal to an angle. Every inverse trig function is equal to an angle. What angle is that going to be equal to? Well, again, in the unit circle, going back over here, we're looking for negative values, so we know they have to be over here because that's where cosine ends up being negative. I know that this location is my radical 3 over 2, radical 2 over 2, and then there's the 1/2. So it's going to be this dash up here, not these two. It's going to be this location. I know that location is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, or you can remember it as 2 pi over 3. So this angle location should simply be 2 pi over 3. Again, if you struggle with doing this concept, it might help if you convert this to be the cosine of theta equals to 1/2. All you're doing is you're applying technically the cosine of this side equals to the cosine of this side. And if we remember accurately that the cosine of cosine inverse, those two values should cancel themselves out. There is a set of properties that follow that rule, and we'll cover that in another video. But this is more or less the concept of how to deal with inverse cosine functions. It's very similar to that of inverse sine functions. The only difference is where the values are regularly accepted for us to get angle measures back.